Okay, so the second part of these notes, we're going to take a step back from the applications and start talking about the exponential functions themselves. And exponential functions are actually just anything that has a number with a variable in the exponent. So we're stepping away from like formulas and everything and just focusing on the bare minimum. So the first thing I want to do is to look at what exponential functions are shaped like. So I'm going to look at two simple functions and I'm going to graph them. And I'm going to pause my video so you don't have to watch me do all of that. I am going to start with the t-chart that has -2 through 2 on the x's. And then I'm going to fill in the y's. Note when I raise a number to a negative power, it flips it. So if you raise 1/3 to the -2nd, it flips the 1/3 to 3/1 and then squares it. So now I'm going to graph those things. Now, I drew both of those graphs. Now you notice how each of the graphs, with like the red graph, on the left-hand side, it flattens out and gets closer and closer to 0. Now if I kept going negative numbers, -3, this would be 1/8, -4, this would be 1/16, I would get closer to 0, but I'd never reach it. So whenever that happens on a graph, whenever we get really close to a number, but we're never going to touch it, we draw something on that graph that indicates that. It's called an asymptote. It comes from the Greek roots and prefixes, a meaning not, sympa meaning touch. And an asymptote is a line you draw on a graph that indicates where a graph will not touch. So the red graph is not going to touch the x-axis because no matter what you plug in for that power, it's never going to reach 0. So I'm going to draw a dotted line on the x-axis that indicates the graph is never going to touch that. That should always be a part of any exponential function you draw. Now, the blue graph is also going to have a horizontal asymptote, but it doesn't touch the x-axis when it goes to the positive side. So that's where I'm going to draw the axis for it. So when you draw an exponential function, it's always going to be increasingly steep on one side, and it's going to flatten out toward a horizontal asymptote on the other. So the growth shape, the decay shape, that. Right. Now, an exponential function is one that can be written in this form, where a is not equal to 0 and b is bigger than 0 and can equal 1. So there are some restrictions on a and b, and it's kind of important to know why they exist. Otherwise, they're just kind of random. If you let a be 0, then this thing becomes y equals 0. That's a horizontal line. That doesn't fit this shape, so it's not exponential. If b were 1 or 0, if b is 0, this becomes y equals 0 again. If b is 1, this becomes y equals a times 1 to the x, which is just y equals a. Both of those are also horizontal lines. And not exponential functions. Now, if b is negative, weird crap starts happening. So if b is negative, let me show you an example. If I were to make b -2, and I were to make a t-chart for this, first of all, -2 to the 0 is 1, -2 to the 1 is -2. When I square it, it's 4. When I cube it, it's -8. So first of all, the points are going here, then here, then here, then here. That's not going to form the shape that we want up here. But even crazier than that, in between 0 and 1, you've got fractional powers, some of which are square roots, which will give you imaginaries. and some of which are cube roots, which will return negative numbers. So you have a graph that's not only jumping around back and forth, but it's also not even connected because it has numbers that don't exist that right next to numbers that give you numbers back. So we just say this is too crazy and the basis can't be negative. All right, now, with that in mind, let's talk about how to graph exponential functions using transformations. So we've always talked about getting a parent graph and then doing the transformations. And remember, transformation rules are, if it's with the x, it affects the x in the opposite way. If it's not with the x, it affects the y in the same way. And those rules have not changed here. What has changed here is how you get the parent function. With exponential functions, the parent function is always whatever your base is, the number that's being raised to the power, to the plain old x. So that can change from problem to problem. So this first one, your base number is 2, so your parent is 2 to the x. On the second one, your base number is 1/3, so your parent is 1/3 to the x. This last one, the thing that's actually being raised to the power is 1/2. So your parent is 1/2, and even though there's a negative on the x, we want it just to the x. That's how you get your parent on each of these. Now, each of those parents has an associated t-chart, but the t-chart changes for each one. We still get it in the same way. You plug in -2, -1, and we raise 2 to each of those powers. So 2 to the -2nd, 2 to the -1st, 2 to the 1st, 2 to the 0, 2 to the 1st, 2 to the 2nd. So I would do the same for 1/3. And again, if you need an explanation of that, that was actually on the last slide. And the same for 1/2. 1/2 to the -2nd would flip the 1/2, make it 2/1, and square it. 1/2 to the -1st would flip the 1/2, make it 2/1, raise it to the 1st. Then anything to the 0 power is 1, and then these are straightforward. So those are the parent graphs. Now I'm ready to do the transformations just as I always have. So when you're looking at the exponential, the big thing to keep in mind is that the x is in the exponent. So anything that's in the exponent is grouped with the x. Anything that's not with the exponent is not with the x. So in this first problem, we've got this x plus 2, and we've got this -3. Remember that 2 base there is part of the parent graph. It doesn't affect any transformations. So on this one, I'm going to be subtracting 2 from all the x's because of that. And I'm going to be subtracting 3 from all the y's because of that. Now, the second one, I'm multiplying by -1 out in front. So, first thing I would do, multiply the y's by -1 because that negative is not in the exponent with the x. And then after I do that, I'd add 1 to the x's and add 2 to the y's. This last one, I'm multiplying by 3 on the outside, and I'm multiplying the x by -1. So I divide the x by -1, which by the same way is the same thing as multiplying it by -1, and I multiply the y's by 3. And then I'd add 2 to the y's. So if you want to pause the video, go ahead and do those, graph them, and then check your answers. I'll come back to you and explain one thing about the asymptotes at the end. Okay, so I've gone through, done all the transformations, drawn the graphs, so I want to make sure my asymptotes are in the right place. So my horizontal asymptote normally starts at y = 0, the x-axis. So the only thing that's going to change the location of that is when the graph has been moved up or down. So if you look at this graph was moved down 3. So my horizontal asymptote then should be at y = -3, which makes sense if I look at my graph, right? It looks like it's leveling off there at y = -3. If I look at my second graph, this graph has been shifted up 2. So my horizontal asymptote should be at y equals 2. And again, if I look at my graph, that makes sense. Now the third graph, it might be a little hard to tell because my points kind of stop in a place where it doesn't look like it's leveling off. But that's why it's good to be able to look at the equation and say, oh, it should be at 2. So now, if I wanted to, I could go ahead and draw this where it looks like it's getting closer but not touching, and then draw my arrow on it. Okay. That should do you on the notes. Be ready to practice this when you come into class on